So we're going to go over some logic before we get into the next parts of the subjectivism section. Some of you may already be familiar with predicate logic and set theory. If you are, a lot of this is going to be a rehash, so you might just want to skip to 2.4b. 2.4b kind of involves some sort of a little bit of complicated logical manipulation, so you might want to brush up in this summary and with Wikipedia and other logic references. I'm just going to go over a quick review of some of the basic terms and concepts in predicate logic. So, curly brackets indicate a set of objects of any kind. What's a set? A set is just a collection of objects, basically. So if I want to demarcate that something is a collection that I'm going to be referring to in formal logic, all I have to do is put curly brackets around that collection of objects. The collection might be the set of numbers 1, 2, 3, or it could be the group orange, apple, potato, and that's a set of vegetables and fruits. It's a set of foods. The above is a set of numbers, etc. Right? Sometimes I want to talk about the things inside of a set, right? And so to talk about those, what you do is you pick out a variable that refers only to the objects in that set, right? And a variable is just something that you can substitute with whatever set it's a member of, right? So if x is a member of the set of numbers, then I can replace x with any number, 2, 3, 4, whatever. When variables are bound, they're called bound variables, and they're bound to things called quantifiers, right? And so in logic, in predicate logic anyway, we want to talk about more than one thing, right? We want to talk about groups of objects. And to do that, what we do is we quantify, we specify the amount of objects that we're talking about, right? So this quantifier here below means for all x. That means for every x in the set of x's that we're talking about, right? In this case, we might be talking about the set of park birds, right? So the birds in a particular park. For every bird in that park, the sentence x is red is true of that bird. That's what this sentence is saying, right? So if you see an upside down A with an x next to it, with an x bound to it, and then you see a sentence after that, that's saying that for every x, which is a member of the set being referred to, the sentence, the following sentence is true, right? The following sentence applies to that x. That's all that a quantifier does. And this is more on the universal quantifier. And remember, you can pause any of these slides in case I'm going too fast, and then just review the concepts specified. I've included some text and some red highlights to denote important terms, right? And so one of the important things here is that the red descriptor in predicate logic is called the predicate of x, right? And x inside of the parentheses, the variable inside of the parentheses of a predicate, a descriptor for an object that's specified in a set, is called an argument, right? And so this predicate takes one argument. Other predicates might take two variables as an argument, two constants as an argument. We're going to be learning more about that. But an existential quantifier is a different kind of quantifier from for all, right? And it basically covers everything else we need to cover, right? So, whereas for all specifies that you're talking about every member of the set, the existential quantifier is specifying that you want to talk about some members of the set. And how do you talk about some members of the set? Well, in this instance, Z might be an element of the set parkbirds, the same set that X was a member of. And Z here is naming a specific object that happens to be blue, right? And so this sentence can read as, there exists a Z such that Z is blue, right? So this sentence is talking about at least one object. It's not talking about necessarily one object, right? There could be two Z's which are blue, right? And then there would exist a Z such that Z is blue, right? So this is saying at least one of the things in the relevant set has the relevant properties specified by the following sentence, right? The following predicates are true of at least one of the objects in the relevant set. So you might have noticed about that sentence, where Z is a particular park bird in the set of park birds, that it contradicts our earlier sentence, right? The earlier sentence was that for all X, where X is a member of the set of park birds, X is red is true of that X, right? So for every member of the set of park birds, that member is red, right? That's actually not true if there's some park bird which is blue. If there's at least one park bird which is blue, then it logically follows, you can infer from that fact, these three dots here mean inference, that it's not the case that for all X, X is red, right? For every park bird, that park bird is going to be red. The dash sign means negation. It means it's not the case that the following sentence, everything that follows this dash line, is true, right? Or in other words, everything that follows this dash line is false, right? And so we're going to start to build longer sentences now, and so parentheses would become useful. Ideally, what we'd have is a parentheses around this universally quantified sentence to show that the whole universally quantified sentence is false. But technically, you could read this without parentheses. So the conditional is a logical tool that allows us to sort of formalize how inferences happen, right? So the previous thing we did, really, was material implication, which is another word for conditional reasoning, right? So we said that there exists a Z such that Z is blue as a sentence. That sentence's truth entails, logically implies, the sentence that it's not the case that for every X, X is red, right? As long as, you know, Z and X are from the same group of things, the set of park birds, the same domain. So all this arrow means, all this conditional means is if the thing on the left is true, if this sentence, there exists a Z such that Z is blue, is true, then the thing on the right is going to be true. That's all that means. So when is this false? This can only be false in one particular set of cases. That set of cases where the thing on the right is false, but the thing before it is just true, right? If that's the case, then it doesn't logically follow that the thing on the right is true, right? And so is this conditional true? Let's see. Well, if there exists a Z such that Z is blue in the set of park birds, then it's going to follow that it's not the case that for every X in the set of park birds that X is red. So this is just the same as the inference before, and clearly it's correct. And rightfully so, since the inference before was correct. This is the same as inferring something. The biconditional, on the other hand, is sort of that, a conditional and its reverse form, right? So if you switch the things on the left and the right, the sentence is still true, is basically what the biconditional does. So in other words, you might read the biconditional as saying two things, right? It's saying that there exists a Z such that Z is blue, implies that it's not the case that for all X, X is red, and if it's not the case that for all X, X is red, then there exists a Z such that Z is blue. It's saying those two conditional sentences, right? Now you might notice that while the top thing is true, the top sentence, like we said before, was true, that sentence on the bottom, the opposite of it, isn't true, right? Just because it's not the case that for all X, X is red, right? That doesn't imply that there's some X that's blue, right? It could be that all of the X's are yellow, right? It could be that every park bird is yellow. Then it wouldn't be the case that any of the park birds are red, but it also wouldn't be the case that any of the park birds are blue, right? So there wouldn't exist at least one blue park bird. So this is actually a false biconditional. And this is more on the universal quantifier. And remember, you can pause any of these slides in case I'm going too fast, and then just review the concepts specified. I've included some text and some red highlights to denote important terms, right? And so one of the important things here is that the red descriptor in predicate logic is called the predicate of X, right? An x inside of the parentheses, the variable inside of the parentheses of a predicate, a descriptor for an object that's specified in a set, is called an argument, right? And so this predicate takes one argument. Other predicates might take two variables as an argument, two constants as an argument. We're going to be learning more about. So a disjunction is what you want to use when you want to use the word or in logic. So when you put this little v in between two logical sentences, what you're saying is that if either thing on either side of this v is true, then the whole sentence is true, right? So for instance, if for all x, x is red is true, then this whole disjunction is true. If there's a z such that z is blue, then this whole sentence is true. And likewise, if both of these things are true, then the whole sentence is true. Right? The only case where a disjunction is false is if neither of the sentences on either side of it are true. Right? In other words, their negations would be both true. On the things on either side of a disjunction are called disjuncts. The things on either side of a conjunction, the thing before, are called conjuncts. Things on either side of a biconditional are called bijuncts, and so on and so forth. Logicians like to have a systematic terminology. You don't really have to remember that. It's just a term that's used to refer to these things occasionally. So nested quantification is what you use when you want to talk about two different objects or more from the same set, the same domain, or from different domains, if you as long as you specify the domains you're talking about, right? So in this case, let's say we're still talking about park birds. We pick an x and a z from the set of park birds, and we'd say that for all x and for all z, right? For any two birds that you pick, right? If z is blue and z is the same color as x, right? That's what this predicate means, same color. Then x is blue, right? So sometimes we want to talk about two different objects from the same domain or different domains. We can also pick different domains. And it basically works the same way as normal quantification, except you're talking about two different objects, and you have to use two variables when you talk about the predicates. And if you can relate them in a certain way, then you can come out with a sentence that uses nested quantification. In this case, we're coming out with an obviously true sentence, right? If two different birds from the same set are the same color and one of them's blue, then the other one's got to be blue, right? Doesn't mean they're the same birds, just means they're the same color. And so you can also use nested quantification to refer to things from different domains. So for example, X could have been the domain humans, right? So it could be that you're talking about for all X such that X is a human, and for all Z such that Z is a park bird. If Z is blue and Z is the same color as X, then X is blue. That also happens to be true for humans, right? So if you talk about humans and park birds and you pick out a human and a park bird from the set, when you substitute, you get that the sentence is true. Note that the predicate same color ZX takes two variables as arguments. So I mentioned earlier that certain predicates might take constants as arguments, or they might take variables as arguments, or they might take more than one variable as an argument, or more than one constant as an argument. We'll get to constants later, but my point here is just that you might come across a predicate that takes two variables, like same color, right? It's saying Z is the same color as X. So all that means is the predicate is talking about more than one object. It's a predicate that relates two or three or four objects, right? Another predicate like that is between, right? You might say X is between Y and Z. That means that it's relating the locations of 3 different objects, x, y, and z. When you see a sentence without any quantifiers, which you might come across, that means that none of the variables in it, if there are any variables, are bound, right? So if z and x were variables here, that would mean this sentence consists of entirely free variables, right? There are no quantifiers in the sentence binding the variables. And so that means that the sentence is saying z is blue and z is the same color as x. That sentence implies that x is blue, right? This is an ambiguous sentence, right? If I wanted to figure out whether this sentence was true, I'd have to know if the sentence is talking about every z, or just some z's, or just some x's, right? Some members of the group. And the reason for that is I'm picking out an x and a z. I'm picking out substitutions, things that can be substituted for any particular entity, right? And it's not clear which entities you're allowing me to substitute for. If you're saying at least one z is such that this sentence is true of it, that's different from saying that, for everything, every bluebird that you pick, this sentence will be true of it, right? In this case, the sentence happens to be true in both cases, right? It doesn't matter whether you're talking about one of the members of the set of bluebirds or all of them, or parkbirds rather, or all of them, the sentence is still true. It's logically necessary, it's obvious. But that's not always going to happen, right? And so you never want to have free variables in a sentence. Sometimes I want to talk about the things inside of a set, right? And so to talk about those, what you do is you pick out a variable that refers only to the objects in that set, right? And a variable is just something that you can substitute with whatever set it's a member of, right? So if x is a member of the set of numbers, then I can replace x with any number, 2, 3, 4, whatever. Right? And we can demonstrate that by using different names, right? So if I said Bob is blue, and Bob is the same color as Mary, and that sentence implies that Mary's blue, that sentence would be true, and it wouldn't be ambiguous, right? You wouldn't have difficulty knowing how to evaluate the sentence, because Bob is a specific person, right? You can't say for all Bobs, or for some of the Bobs, or for some of the Marys, or for all Marys. That's nonsense. Mary and Bob are 2 specific people, and we're talking about properties that those specific people have. Likewise, the set of objects that Bob and Mary belong to is irrelevant, right? Because, or rather, we don't really need to specify the set using a quantifier, because we're not picking objects from a set. Bob already comes from a predefined set. Bob is a name for somebody. Either that person is a person, or they're a bluebird, or they're a parkbird, or they're a number, or whatever. It's just a name that someone's already given, so the set has already been defined. Likewise, constants and names in predicate logic are always lowercase to distinguish them from functions and predicates, right? In this case, we have predicates only, so it's sort of hard to see the use for the distinction, but trust me, it sort of gets confusing when you use a bunch of predicates and names. So always capital letters for predicates, always lowercase for names. And I think that's all we need for this refresher.